Hey, we're looking at radicals and roots today, and we want to start out by comparing this to exponents, to taking a base and raising it to a power. So, for example, let's say we start out with the number 2. Okay, I want to take 2 and raise it to the second power. What am I going to get? Well, that's 2 times 2. Well, that's just 4. I could do the same thing for the number 3, right? 3 to the second power is the same as 3 times 3. That is 9. Okay, so exponents and powers, we've covered this before. Nothing too new there. But I want to think about, how can I reverse this? How can I undo squaring a number? Well, it turns out undoing that is going to be the square root. What I mean is, if I start with the number 4 and I take the square root of 4, I'm going to get 2 back, right? So I get back my original base. Likewise, I can take the square root of 9. What does that give me? Well, it's going to give me 3. It'll give me back my original base, just like that. So what we see here is, essentially, we're creating the inverse operation to taking something and squaring it, right? This is similar to how subtraction is the inverse operation to addition, and division is the inverse operation to multiplication. The square root is the inverse operation to squaring a number. Okay, so that's the idea here. And this symbol here, this little special bracket symbol, that's what we call a radical. And when we don't write anything else here, we're assuming this is the square root. But to be explicit, you can, if you want to, add a little 2 sort of inside that little corner there, inside the radical. And that's going to explicitly describe a square root. But if you don't write the number 2, it's implied it's a square root. So here's sort of the general rule, right? We're saying that the square root of a equals b when a equals b squared. And that's exactly what we have right here, right? The square root of 9 is 3 when 9 is equal to 3 squared. Okay, so that's the general rule here for square roots. But notice this extra condition. We're saying that b is going to be positive, right? That means this number here is always going to be positive. It's not going to be a negative number. I guess it could be 0, okay? But besides that, it's going to be positive. Why is that? What's going on? Well, let's think about this, okay? When I take a number, let's say I take the number 2 squared, that's going to give me 4. And so it makes a lot of sense for me to say, well, then the square root of 4 should equal 2. No problem. We understand that. But what if we take negative 2 and square it? What do we get? Well, negative 2 times negative 2 is also going to be positive 4. So shouldn't this imply then that the square root of 4 is equal to negative 2? It turns out it doesn't work this way. Just by definition, we can't do that, okay? We're not going to get a negative here because this positive 2 here, this is what we call the principal root, okay? And so even though 4 can be formed by 2 squared or negative 2 squared, when you take the square root of 4, you're always going to get a positive number. You're always going to get the principal root, in this case, 2. If you wanted to get the negative root here, you would literally have to negate that radical in the beginning, and then you would get negative 2. Okay, so we're always expecting a positive number there. So this actually brings up an interesting question. What would happen if I took the square root of a negative 4? What would this give me, right? So what this means is there must be some number, let's call this x, that I can square to give me a negative 4. What could I do? Well, I can't do 2 squared because 2 squared is going to be a positive 4. And I can't do negative 2 because negative 2 squared is also a positive 4. So it turns out there is no real number that I can square to give me a negative number. This is impossible. I would have to invent a whole new kind of number in order to make this work. And actually that's possible. We can do that, and we're going to talk about that later. But for real numbers, this is not possible. So we cannot take the square root of a negative number. And when we take a square root of a positive number, we will always get a positive number back, the principal root out. We will never get a negative number as a root. We'd have to actually negate that entire radical. Okay, so that's just an introduction here to sort of square roots and how they are the inverse operation to squaring a number, to raising a base to the power of 2. Okay, let's take a look at how we can generalize this. What I want to think about now is the concept of the nth root. So going beyond the square root, what if we can take sort of the nth root, right? Let's write down a couple of numbers here. Okay, so let's go 1, 2, 3, 4. Okay, so let's say I have 2 and I want to raise it to the first power, the second power, the third power, and the fourth power. Okay, what am I going to get? Well, 2 raised to the first power is just going to be 2, right? 2 times itself just one time is 2. What about 2 squared? Well, that's going to give me 2 times 2 is 4. 2 cubed? Well, I'm going to multiply this 4 by 2, so that's going to give me 8. Another power of 2, I'm going to multiply this 8 by 2, that's going to give me 16. Okay, so far, no problem. Now let's think about how we can get the inverse operation here. Okay, the inverse operation would essentially be, in this case, it would be sort of the first root of 2. What's that going to be? Well, that's going to give me 2, right? It's sort of the identity. One is the identity here for powers and for roots, because 2 raised to the first power is 2. And so if I take the first root of 2, I'm going to get 2 back, right? That's the idea. Okay, so what if I try now taking some root of 4? I'm going to take the square root of 4. What am I going to get? Well, now I get 2, right? Because 2 squared is 4. That's the idea. Let's continue to generalize this. Let's take now a root of 8. Let me take the cube root of 8, and this is going to give me 2, right? Because 2 cubed equals 8. And finally, I could try taking the fourth root of 16, and guess what? This is going to give me 2 because 2 to the fourth power equals 16. Okay, so this is how we can treat the nth root as sort of the inverse operation to taking a base and raising it to the nth power. Right? We can sort of generalize this. We can say that any 2 raised to the nth power, let's say that equals x, right? Well, then that means that if I take the nth root of x, I'm going to get 2 back out. Okay, so this is the idea behind the nth root. Let me give you the general rule here. The general rule we're saying is that the nth root of a will equal b, and that's when a equals b to the nth power, okay? But there's a little caveat here, and this is that for even powers of n, for even powers or even roots n, we can only have positive values for a and b. Okay, now why is that? Why is that true? So let me write down a bunch of negative 2's this time, right? We want to deal with negative numbers, 2, 3, 4. Okay, so imagine we take negative 2 to the first power, the second, the third, and the fourth power. Okay, what are we going to get? Well, negative 2 to the first power, that's just negative 2, right? Negative 2 squared, well, that's actually going to be 4, isn't it? Negative 2 times negative 2, the negatives cancel. So anytime we have an even number of negative signs, they cancel out, we get a positive number. Well, here we have an odd number, so actually we're going to take this 4 multiplied by negative 2, we're going to get a negative 8, and then negative 2 to the fourth power, we'll take this and multiply by a negative 2, that cancels out the negative sign, and we'll get a positive 16 back. Okay, so we kind of start to see this pattern developing where even powers of n will guarantee you get a positive number here as a result, okay? And that's just because anytime you take a negative number, if you have an odd number of them, you have here just 1, negative 1, that's going to be negative 1. But if you have 2, well, the negatives cancel, you're going to get a positive 1. Multiplied by 3 of them, well, now it's going to be an odd number again. Multiplied by 4, an even number, now it's a positive number again, right? So positive numbers are guaranteed when you have an even power. Okay, so now let's take a look at finding the roots here, right? So what we can do is we can take essentially the first root of negative 2, right? What's that going to be? Well, that's just going to be negative 2, right? We're just inverting this, and that's certainly possible. I know that negative 2 to the first power is negative 2, so that's going to come out here. What if I take now the square root of 4? What's that going to be? Well, we did that before. That's going to be positive 2, the principal root, right? So here, n is even. Inside, it has to be positive, and this result must also be positive. We're getting the principal root. That's what this rule is stating, right? Let's just finish this up here. So let's do the cubed root of negative 8, right? What's that going to be? Well, that is actually going to be negative 2, okay? So for odd numbers here, odd roots and odd powers, we can have negative results. And finally, let's take the fourth root of 16, just like on the other side there, we're going to get a positive 2. Okay, so that's what this general rule is talking about. It's just because when you take even powers of a negative number, you're guaranteed to get a positive number back. All right, let's take a look at some of the important rules now for roots. For our first rule here, we're going to see something that should remind you of one of our exponent rules. So this should look very similar to when we had some a times b raised to the nth power. We saw that you could essentially sort of like distribute that n in, and what you would get is a to the n times b to the n. And you can see that's pretty much what we're doing here with the nth root. Okay, so let's look at an example. Let's take the square root of 16. Okay, what's that going to be? Well, that should be 4, okay? Square root of 16 should be 4 because 4 squared is 16. But we can try and decompose that 16 into a 4 times a 4, just like that. And so this is telling me this is the same as the square root of 4 times the square root of 4. And of course, the square root of 4 is 2, so that's the same as 2 times 2, which is equal to 4. Okay, so it does work, right? So 4 here is, in fact, equal to 4. Okay, so that one works. Let's try another one. How about the square root of 36? Okay, so the square root of 36, I should get the number 6. That's what I'm expecting. Let's decompose this 36 into, how about 4 times 9, okay? And if I do this, well, I can say this is the same as the square root of 4 times the square root of 9 using my rule here. Square root of 4 is 2. The square root of 9 is 3. 2 times 3, well, that is 6. So again, it works. Okay, so that's the first rule here. Let's look at the next one. This rule here should remind you of one of our other exponent rules where we had some a over b raised to the nth power. And we saw, again, you could essentially distribute that n in and get an a to the n over a b to the n, right? And so we're doing kind of the same thing now here, just with roots instead of powers. So let's look at an example. Let's take, how about the square root of 4 over 9, okay? What we're saying is that you can split this up into the square root of 4 over the square root of 9. Square root of 4 is 2, square root of 9 is 3, so it should be 2/3. And we could check that, right? Because taking the inverse operation should tell us that 2/3 squared should equal 4/9. Okay, so this is the same as 2/3 times 2/3. And yeah, sure enough, multiply the numerators, you get a 4. 3 times 3 is a 9. So yeah, that works out. Okay, so that's all we're talking about right here. Let's do one more example. Let's try, how about a cubed root of 8 over 27. Okay, what's that going to be? Well, we can split that into the cubed root of 8 over the cubed root of 27. The cubed root of 8, well, that's going to be 2, right? Because 2 cubed is 8. 2 times 2 is 4. 4 times 2 is 8. Okay, so that'll be a 2. And the cube root of 27 is going to be a 3, right? 3 times 3 is 9, times 3 is 27. Okay, so 2/3. And we could cube this, right? We could take 2/3 cubed, and sure enough, this will be the same as 2/3 times 2/3 times 2/3. And 2 times 2 times 2 is 8, and 3 times 3 times 3 is 27. So yeah, it works out. Let's look at the next rule. Once again, this should remind you of one of our power rules where we had some a to the m power, and that was all raised to the nth power. And here, essentially, you can multiply these two exponents together. You would get a to the m times n, right, to the mnth power. And that's basically what we're doing here, right? We're going to multiply the roots here together and get a single root at the end. Okay, so let's try an example. Let's try taking the cubed root of the square root of 64. Okay, what's that going to equal? So let's do the inside part first. So the square root of 64 is 8, right? Because 8 times 8 is 64. So this is the same as the cubed root of 8. And we already saw that the cubed root of 8 is equal to 2, because 2 times 2 times 2 is 8. 2 cubed is 8. Okay, so let's use this rule now. Okay, so if we were to use this rule, this should be equal to 3 times 2 is the 6th root of 64, right? We want to see if that is equal to 2. Okay, how do we do that? Well, let's think about it. 2 squared is 4. 2 cubed is 8. 2 to the 4th power, it's going to be 8 times 2 is 16. 2 to the 5th power, well, that's going to be 16 times 2. It's going to be 32. And 2 to the 6th power is going to be, sure enough, 64. Okay, so yeah, that works. The 6th root of 64 is 2. Okay, so that's the idea here. Let's try one other example. How about we take the square root of the square root of 81. Okay, what's this going to be? Well, if we do the inner square root first, that's the same as the square root of 9, and that is just going to be 3, because 3 squared is 9. Okay, so let's do it using our new rule here. We could think of this as essentially a square root, right? So that's a 2 inside of a 2 here. So we can think of this now as the 4th root of 81. And we want to see if that is also going to be 3. So let's check. So 3 squared is going to be 9. 3 cubed is going to be 27. 3 to the 4th power, well, I can't do 27 times 3 in my head, but I can think of this as 3 squared squared. And 3 squared is 9. So 9 squared is 81. So sure enough, this works. 3 to the 4th power is 81. So the 4th root of 81 is 3. Okay, we've got another rule coming up. Here we've got an interesting rule here. What it's showing us is that essentially you can think of when you take the nth root of some number to the nth power, the root and the power sort of cancel out and you're just left with whatever number you started out with here, okay? So let's see if we can show you how this works. Now remember, just the idea of an nth root, right? The nth root of a equals b, that's when a equals b to the nth power, right? So, okay, let's do an example here. Let's do the cubed root of 7 cubed, okay? Hopefully this will equal 7. But I don't know what it is, so let's just say this is equal to b, right? It's just equal to b. The cubed root of 7 cubed is equal to b. So if that's true, that means that 7 cubed, right? Whatever's in here, this is what's inside here, must equal b cubed, right? That's just the definition of taking the nth root, the cubed root here. And the only way for this to be true is if b is 7, right? And that's what we're trying to show. We're trying to show that you get just 7 out afterwards, right? We're trying to show that if you do this cubed root of 7 cubed, you can essentially cancel out these cubes and just get a 7. And that's what we get, okay? Let's try one more quick example here using, how about we'll do the cubed root of -2 cubed, okay? So if we do this, what do we get? Well, this is basically the cubed root of, well, it's -2 cubed. It's going to be -2 times -2 times -2. That's -8. And the cubed root of -8 then will be -2. Okay, so once again, we get this this original number that's inside here back out. Okay, the cube and the 3rd power, they cancel out. Okay, let's look at the very final rule here, and that is where we see what happens if this is not odd. If this is even, what's going to happen? So the even rule here is a little bit different because now we've got this funny absolute value sign. Why is that? Well, I think you probably have an idea because we can't get negative numbers out when you have even roots or even powers. Okay, that's the secret here. So let's try this out. What if we're taking, say, the square root of 4 squared? Okay, what are we going to get here? Well, that's going to be the same thing as, say, the square root of 16, and the square root of 16 is just 4, which is fine. That's what we expect to get, right? We should just be getting this 4 back out. We should have these 2's sort of cancel out, and that's exactly what's happening, right? But let's try it now with a negative number, okay? So if we take the square root of negative 4 squared, okay, now what do we get? Well, negative 4 squared is positive 16. So now we're getting the square root of 16 again, and the square root of 16 is positive 4, right? And so there is no way for us to get the negative 4 back out here, right? So instead, what we're going to say is this negative 4 is equal to the absolute value of negative 4, right? This positive 4 is equal to the absolute value of negative 4. This positive 4 is also equal to the absolute value of this 4 in here. And so if you take the absolute value, then that's always going to be true. Okay, so that's the idea here. Just because anytime you take some number, raise it to an even power, you're going to get a positive number. And then when you take the square root of a positive number, you're going to get a positive number. So you can never get this negative right back out again. Okay, so that's the idea on how we can do nth roots. We can see that roots were essentially the inverse operation to taking something to a power, to an exponent. And then we looked at a whole bunch of different rules that are very, very similar to the rules for exponents that we already learned. Okay, so come back next time and we'll do a bunch of practice problems because working with roots, it can be a little bit tricky. I'll see you then.